Let's just start and try and find a way of explaining to each other how do you find the defining equation of a cubic graph, which means if somebody draws the graph for you and they ask you to find the defining equation for that particular graph, how would you actually do that? Well, there's many different questions you might get or different ideas that you can engage when you're trying to find the defining equation of a cubic graph. But I just want to draw your attention to three popular cases that might help you in terms of thinking around finding the defining equation. Before we even go far, you guys need to know that the defining equation of any cubic is given by the form y is equal to ax cubed plus bx squared plus cx plus d. So this is the general defining equation of a cubic function. When you have found the equation, it must end up there. Now, how would you actually go about finding the defining equation under these three different cases? Let's first of all zoom in on the first case, which is the case where your graph happens to cut the x-axis 3 times, which means when it has 3 unique x-intercepts, the graph will probably look something like this. Imagine this setup where you've got your graph cutting the x-axis 3 times at, first of all, the first x value, which is this one here, which I'm going to call my x1, and another x value here, which is my x2, and lastly, that x value there, which is going to be my x3. So when you've got those 3 unique x values, and in addition, you happen to have a random point anywhere on the graph, if you've got a random point with the coordinates x and y, what is the approach of finding the defining equation under these circumstances? Right, so what you will do is you will then go and do this. You'll just say y is a into x minus x1 into x minus x2 into x minus x3, where your x1, x2, and x3 will happen to be these x values that the graph is simply cutting through. And then the x and the y is what you will substitute for this x here and that y in order to figure out what your a value is, and then from simplification you'll end yourself there, which is where we are right now. So the important thing you need to remember is that this will simply be the number you're going to substitute there for x1, and this one you're going to substitute it there for x2, and this one you're going to substitute it there for x3. And then after that, this x and y is just what you put for this x you see here, and the y is what you put for y, and then you can solve from there. The second case is different from this one. The second case is the case where you still have your graph, but your graph happens to cut only 2 x values, such that on the other x value it's turning at the same time, which means something that looks like this. It is going to cut through this point but passing through the other one explicitly. However, on this one it's not cutting through, it's just turning on it. So this is what I refer to as the bouncing point. The graph bounces when it gets there, it's not cutting across through. So this is what I'll refer to as my x1, and this here is simply my x2. The y value can be, the y axis can be anywhere. You could probably have the y axis anywhere where you want. And again, we could probably have another random point here anywhere on the graph, which I'm going to call x and y. So when you have a situation like this where you've got 2 x-intercepts, not 3, and then one of them happens to be a stationary point or a turning point, how do you find the defining equation? Well, you simply do this. You just go to your paper and then you write y equals to a into x minus that x1 you see there squared into x minus x2. So I'm squaring this one because it is a repeating factor. Normally when a graph does this, it means at x equals to x1, the graph is repeating itself. It means it's a repeating factor. So that's why I have x minus x1 twice. So that point that happens to be a turning point or a bouncing point will always be appearing 2 times because of the fact that it is a turning point and an x-intercept at the same time. Right. The last case is the case where, you don't have x-intercepts like here, and you also don't have x-intercepts like what you're looking at right now. But what you simply have is the turning points or the stationary points of the graph. So anyone can draw a cubic, for example, a cubic such as this one. Let's just say I have got a random cubic that does this, and the y-axis can be anywhere. Again, we could probably have it there, doesn't matter. The important thing is nobody tells me what the x-intercepts are, but I am given the turning points, the coordinate of the turning point, this coordinate of the x and the y coordinate, and then here I've got again the x and the y coordinate. So what is the approach of working with a question such as that one? Well, The approach would just simply be for you to find the defining equation. You can't use this format or even this one because the x1s and the x2s are x-intercepts and you don't have them in this case. But what we know is at the turning points, the gradient of the graph is 0. At the turning point, the gradient of the graph is just simply equal to 0. Even here, at this turning point, the gradient of the graph is equal to 0, which means that the derivative of this graph is equal to 0. So you will need to go and take that and write it down as y is ax cubed plus bx squared plus cx plus d, and then from there you find the derivative of that function, which means you'll then go and do dy over dx is, you then have 3ax squared plus 2bx plus c, and then that must be equated to 0 because this gradient or this derivative you're looking at here at the turning point is equal to 0. So you'll then say, okay, my 3ax squared plus 2bx plus c must be equated to 0 because when the graph increases, its gradient is positive. When it's decreasing, the gradient is negative, but at the stationary point, the gradient is just equal to 0. From there, those x values you see, these ones, this first x value here, you will take it and replace it everywhere where you see x here, right? That will give you one equation. And then you go get the other x value at the turning point, you replace it where you see x. That should produce the second equation for you. With those two equations, you can then solve simultaneously to try and simplify. You'll eventually end up with what you're looking for.